Let's do problem 15 on page 731 of chapter 23. There's one very similar to this on the take-home test. So I want to go over it, and I think there might be one like on the exam where you have to do something like this. But anyway, I'll read the problem. It says, in the figure shown, determine the point other than infinity at which the electric field is zero. So here's what we've got. We've got a negative 2.5 microcoulomb, charge here. I'll call this Q1. And then we have a 6 microcoulomb positive charge right here. I'll call this Q2. Now, where is the field zero? So remember, let's think like a positive test charge. So let me redraw this. I'm going to put the negative 2.5 microcoulomb charge here. And I'm going to make an x-axis. And I'm going to say that this is the origin right here. And so 1 meter away is the 6 microcoulomb charge, Q2. Now, I want to know where along this line. First of all, if you're off the line, the electric field from these two charges cannot cancel out. Right? You need the electric field from the two charges to cancel out. Okay, so if you're off here, then, a positive test charge, it'll be attracted to this, repelled by this, and there's no way that, well, I didn't draw that very well, but there's no way that these two electric field vectors can cancel each other. So, anywhere, any region in space out here, the electric field is not going to be zero. Well, let's look along this line. If I'm right here, I got a shot because I'm going to be repelled by a positive test charge will be repelled by the 6 microcoulomb charge, and it will be attracted to the negative 2 microcoulomb charge. But here's our problem. Anywhere, as long as we're to the right here, we're always going to be closer to the positive charge than the negative charge. And since the positive charge has a greater charge than the negative charge, there's no way that this is the E field from 1. The E field from 1 will always be less than the E field from charge 2. If you're to the right, this will always be true. The electric field from 1 will be less than the electric field from 2. So they can't be equal, E2 will always be greater than E1. They can't cancel each other out. Does that make sense? So this eliminates this whole region of space from along this line. Well, let's put a positive charge in between them. And now, here's the problem. If I look at the E field from 2 and the E field from 1, they're both going to be to the left. So they're always going to add up. They're never going to cancel each other out. So there's no region in space in between them that will be equal to 0. But if I'm over here, I can be attracted to the negative charge, and I can be repelled from the positive charge. And this is closer, so even though the negative charge has less overall charge, it can still, because we're closer to it, we can still find a place where they will actually, the two electric fields will be equal to each other. And so what I'm going to do is find that position, and where I go, okay, so this is E1 is equal to E2. Now I'm going to say the magnitude of E1 is equal to the magnitude of E2. We know they're in opposite directions. So the magnitude of E1 is KQ1 over its distance squared, where I'm going to call this x squared. equals K Q2. Now we're dealing with the magnitudes of these charges. You don't put the negative charge in anymore. And this is going to be x plus 1 meter squared. From the positive test charge to E1, it's whatever x is plus 1 meter. So the k's cancel, and take the square root of both sides. You get root Q1 over x equals root Q2 over x plus 1 meter. Now, oh shoot, I only got a couple of minutes left, but it's just a matter of solving for x. And I did a little differently algebraically here, and it's kind of messy. But, so I took this, actually I cross multiplied, then I took the square root of both sides, and then I solved for x, and you get, in terms of the charges, and you get this. Now remember, the 1 meter is in here. So you have that 1 meter right there. Otherwise, you won't get a meter for an answer. You plug the charges in, and you get 1.82 meters. So x equals 1.82 meters. But remember that we stipulated that this value for x is to the left. So it's 1.82 meters to the left of the negative charge. That is all.